so last time we asked this question, what's LZ squared, and we ended up with this. So what was the benefit of that? Well, we can now talk about our Schrodinger equation in two different ways. So we can express our Schrodinger equation, in two ways. We have that LZ squared over 2I, or we can represent it as negative h bar squared 2I. I think we need M in there. No, we're okay that way. Phi psi is equal to E psi. Personally, I like the second way more, so we're going to go along with it. I think your book goes along with it. All right. So awesome. We have a Schrodinger equation, but we got to try and solve this thing. We want to determine what psi is for a particle on a ring. Okay, so we have this expression. Negative h bar squared over 2I phi squared psi is equal to E psi. However, this is a little difficult to solve for. What would you do, or what have we done in the past? Or what have you done in your differential equation classes to try and solve a problem like this? What would you do? Or out of this equation, what part's the most difficult to solve for? Like, is this tough to solve?
No.
No.
Is this tough to solve?
No.
No, because that's a constant.
And so it's the b squared side.
Yeah. So let's isolate that guy by itself because it's difficult to deal with. So we can rewrite this. So yeah, psi squared is equal to, what's this side going to become?
2IE over negative h bar squared times psi.
Yep, E psi. Okay. And what this tells us is we have to have a quantized energy. So we get a quantized energy. Meaning, what that word quantized, what does that mean again?
Discrete.
What was that?
Like it's a discrete number,
Yeah.
so
Discrete.
it's like an integer.
Mm-hmm. Has to be, well, it just has to be a specific value. Can't take on like a continuum. Okay. So what about psi? That's the thing that we don't know yet. So basically this equation up here, we can simplify that a little bit. What do we know about this expression right here?
Constant.
Yeah, it's a constant. So how about we just say, we put a k in here. We're going to put k squared for reasons I'm not going to tell you quite yet, but it'll become apparent. Let's say it's just equal to that. So there's a solution to this equation. So a solution to this equation is, anybody have an idea of what it's going to look like? What are almost all the solutions to our equations in this class?
E to something.
Yep, e to something. So let's do our wave function, which depends on phi, is equal to a e to the I k phi. And we'll start with that. Okay, so we have a generic form. What's the next thing we always do with our model system? Or what would we do with particle in a box? We figured out the Schrodinger equation. We had a basic form of an equation. What did we do after we had that basic form of the equation?
Like looked at the parameters.
Yeah, looked at the parameters, we looked at the bounds. So let's check out the bounds. So again, remember we're talking about a particle on a ring. Let's zip it around. We have that radius r. We had our coordinates. Oh wait, you guys don't like it that way. You like it this way.
Right, right.
Boom, roasted.
He doesn't like
And
it.
then we had that angle, right? So let's think about some bounds that we have. So this particle is zipping around. It's stuck in that ring, right?
Does the angle that we measure matter? Like, could it be to the x also, or is it
Yeah, it could be to the x or it could be to the y.
okay?
Most people do the x. Put those there so this thing quit spazzing out. There we go. Okay. So we have to think about what parts are going to be the same. So this particle keeps traveling around in a circle, right? Phi is changing, r is not, though. So what do we know about this particle as it's going around in a circle?
We move at a constant speed.
We don't quite know that because it's a quantum system. They behave really weird, right?
It will always stay our distance from the center.
Yep, we're always at a distance of r. What about if I start at this point and I zip around and I end up back at that point? I've gone one full rotation.
No displacement.
Yep, there's a zero displacement. But what about this angle? This angle went from, let's say it's at phi to phi plus 2 pi, if we're talking about it in terms of radians. So I think one of the things that we should be looking for is that the value of the wave function should be the same at this point, no matter if we're at phi or at 2 plus phi. Does that make sense?
Yeah.
On a circle, the particle retraces its path. After how many degrees in a circle?
360.
Yeah.
2 pi.
Yep. Or 2 pi radians. The world of radians, man. Okay. So therefore, we want our wave functions to be the same at that point, no matter if the rotation's been just phi or phi plus 2 pi. So we want to say that these two are true. Okay, so in order for that to be true, let's go, we have our generic equation up here. Let's put in these two values. So we have to have A is equal to the E I K phi, and we also have to have A, this expression has to be equal to E to the I K phi plus 2 pi. Okay. What can we do with this expression? How can we simplify this?
Get rid of the A's.
Yep, get rid of the a. So we're left over with e to the I k phi.
ln it.
We're not going to ln it yet. We could ln it, and that would make our lives a bit easier. But we want to. We're going to see through Euler or Euler's method that this is going to break down into sines and cosines. Okay. Sorry, I'm using my cell phone to turn down my heat. I don't know what is going on. But
Oh, do you have a Nest?
oh, yeah. So probably, I don't know, the heating company keeps jacking it up. But I'm boiling alive. There we go.
In there too.
Or it's my wife just constantly cranking it up. Okay, so with this, we can split this apart into e's also. We could have this expressed differently. How could we express this guy?
E to the I k phi, or no, yeah, yeah. And then also times e to the I k 2 pi.
Yep. Okay. So now we have this expression. We have e to the I k phi is equal to e to the I k phi times e to the I k 2 pi.
Oh,
So how can we simplify this?
so those are gonna have to equal 1.
Yep, get these, they'll just go away because we can divide it through. And we get 1 is equal to the I k 2 phi, which doesn't look like it's helped us out too much because what this shows is this is just a constant. How does that really help us? Well, that's where we start using some tricky math. We're going to go jump back here.
As opposed to the easy math we were using.
Yeah. Actually, I was listening to that lecture with Paul Dirac, and it was kind of interesting because he was talking about how Heisenberg was using matrices, but he had never seen them before. No one had ever used matrices before, like in physics. So they had to all learn this new math, and they were irritated because they liked algebra so much and it was way easier. Then they went to this matrix stuff and was like, this is hard. So if you're ever feeling down on yourself, think even like Paul Dirac and like Heisenberg and all those guys were confused by matrix math. So you're ahead of them right now.
What happens if we're also confused by algebra?
I don't think that's true. So if we go back to e to the I phi, oh, actually, let's not do phi. Let's do e to the I theta. Do you remember how to express that in terms of sines and cosines?
Cosine plus sine.
There is a cosine, theta, plus there's another term.
Oh, it's I sine theta.
Yep. Sine, theta.
Is
Okay.
that phi or theta?
Here, this one, that's an I, these are thetas.
Yeah, up there.
Oh, up here?
No. Yeah.
Oh, you're talking next to E. Yeah,
That's meant to be a theta. There's an I theta there.
It's confusing.
Even though that looks
they ain't
like
getting too used to drawing the phi.
Donut with a belt.
yeah, theta, my bad.
It's like an Easter egg.
So our expression.
Donut with a belt or donut with a sword? We could use those terms, please. Yeah.
Belt and sword.
Or a stick.
Okay. So let's go, we came to this expression. Oops, which I can't see that guy. So we have e to the I k 2 pi. Using this Euler's theorem, how are we going to express this guy?
Well, it's going to be cosine that 0 with the line through it plus.
So what's, in our case, in this equation, what is our theta?
K 2 pi.
Yeah. So we have k2 pi plus I, what else do we got?
Plus sine 2k pi.
I'm going to write it this way. Okay. So looking at this, can we get rid of any of these terms?
One of them's 0, I think.
Yep, one of them will be a 0. Which one's going to be a 0?
First one.
Sine term.
An integer.
2 pi.
We want this sine term to be a 0. Why do we want this one to be 0?
The I.
Yeah.
Yeah,
But it is because
I.
it's 2 pi times some constant. So.
I
Is
mean, the
K,
constant could
is
be
K
a
an integer?
fraction.
Oh, shoot.
What were you saying,
It's not
Josh?
that easy.
Is K an integer or is it a,
We haven't put anything on K yet.
okay, because it doesn't necessarily make it 0.
Right. But we do
Nice
want
one.
this, we want this to be 0. And Tara, I think you said why this should be a 0. What did you say? Why did we want this term to be 0?
Because of the I.
Yeah, this I. It's imaginary. Imaginary numbers really don't mean too much. So, so sine must be term, or sine term must be 0. We want no imaginary part. And more importantly, if we look, this value has to be equal to 1. Does anyone see an imaginary part to that?
No.
I don't. There's probably some crazy mathematical theorem that says the I is like 1 or something. We're not going to worry about that. All right. So therefore, we need this expression to equal 1. When is this equal to 1?
Zero, not 0. Equal, yeah, equal 1 and 0. So if K was 0,
Yep, cosine is equal to
1. So yeah, 1, 2, 3. It's gonna equal 1.
Oh, so you're
Is
saying
it equal -1 when it's 2 pi? Or is
yeah, so if we do -2 pi, that's also equal to 1, right? Cosine of +2 pi is equal to 1. What other cases would this be equal to 1?
Cosine of 4 pi.
Yep.
So 2 pi n?
-4 pi also is equal to 1. Okay, so now we have to think of ways. So therefore,
I almost said of -0.
so we said this has to be equal to 0 plus or minus 2 pi plus or minus 4 pi, right? So what can you think about for values of K? To make this work out.
Any positive or negative integer? What?
And that also includes what?
Negative.
So positive or negative integers, right?
Yeah, so we got plus or minus 1, plus or minus 2. There's also one more number.
0.
Yep, 0. Is 0 an integer?
Oh, no, it's not. All right.
Okay, so it follows this pattern. However, K is way too generic. Since K is too generic, we give our constant a new symbol. Anybody know what that new symbol is?
Is it something Greek?
Nope.
No.
Was
Oh.
it the M of L from the?
Yep.
Zeta.
N sub L. So this is pretty cool. We found 2 of the quantum numbers so far. We found N and we found N sub L. N comes from just having quantized energy. N sub L has quantized angular momentum. So we found 2 sets of quantum numbers so far. Okay, but what does that make our expression? So let's go back to our wave function. It's dependent on phi. What else does it depend on? Depends on that value of N sub L. So we get A, E. What's the rest of this going to be? Or what did we say our wave function expression was? That it has like a generic form that looks like this, right? So what's ours going to be?
Cosine of 2 pi ml, is that one? Or no,
Nope, don't
right
even need cosines. We're just going off of this one. We're making this one less generic.
now?
So,
So IML
yep,
phi.
exactly. Okay, cool. So we have a form of our wave function. What do you think we need to do next?
Normalize it.
I'm sorry, what was that, Maddie?
Nothing.
Well, what do we know in here? What don't we know?
Don't know A.
Yeah, we don't know. How do we find out?
Probably was it normalized?
Yep,
That'd be
we're going to normalize it. And now we need to determine A.
That's actually what I said.
See, have more faith in what you're saying.
No.
Through a normalization. Whoa, we're going to try that again. Normalization. Woo! Big exclamation point. Okay, how do we normalize the function again?
Let it equal to 1.
Yep. So 1, let's do it generically first. 1 is equal to what?
Integral of
Integral, yep. What are we doing?
phi star times phi
Bless you.
tau.
Psi star, psi d tau. Okay. All right, so for our expression, what are our integration limits?
0.
Was it like 0 to 2 pi?
Yep, because we're talking about a circle. Good. We have a e to the I k, or oops, excuse me, I m l phi. We got to take the complex conjugate of that times a to the e I m sub l phi. And what are we going to integrate over?
Shouldn't one of those be a negative?
Yeah, I left the star there. Well, we're going to talk
For
about that.
now,
I don't know.
What about our integrand, or whatever this is called?
the
Mhm.
sword.
The sword.
I.
Yeah, that's sword, right?
Yeah.
Okay. So, and Josh, you were saying you were getting ahead of me, which is good. What's got to change with this expression since we're taking a complex conjugate?
Gotta just make it negative.
Yep. So in most other wave functions, we haven't had an I, so keep track of that. That's increasingly important also for expectation values in other parts. Okay. So now we got what? A to the E negative I K, not K, M sub L phi A E to the I M L phi. Okay. How can we simplify this expression? What can we do?
Can you bring the
Take out an a squared.
Yep, take out an a squared. What else? Or let's just do that for now.
Those two
You
a
just cancel out.
e terms just gonna be 1.
Yep.
Just equals 1.
Welcome to the easiest integral we're going to do in this class.
Heard that before.
What's this going to be then?
True, true.
It's just 2 sword times x squared.
Yep. 2 pi 5.
God, my sister's so loud. I couldn't hear her.
I'm sorry.
What'd you say?
Uh,
Did you
I don't
hear
hear
her talking?
We haven't heard her. At least I haven't.
Okay. I'm gonna call her and say happy birthday coming to Zoom.
She's teaching in the living room and she's so loud.
Okay, so what's A gonna be? This is all equal to what then?
One.
Yep,
No.
1. So what's A equal to?
Oh, it's 1 over 2 pi. It's the square root of 1 over 2 pi.
There we go. Cool. So now, what's our normalized wave function?
Square root 1 over 2 pi
Mhm.
e I ml donut with the sword.
Sword donut. That sounds way cooler than it actually is. So, so our normalized wave function. Since we've been stuck inside, my wife has been craving donuts from Reed's, and they make them like fresh.
They're really good.
But like I went to Reed's over the weekend, and I just saw like people coughing and like putting their hands in there, and I'm like, nope, can't do it.
Oh, come on.
But I want one so bad.
A little lemon thing.
Rub it down with some bleach. Yeah.
Yeah, exactly. Just clean them up.
Spray some with some
Yeah.
Lysol or something like that.
That's good for you.
All right, and now it can be shown that the energy is, and you guys found this expression for your daily problem, E m sub L is equal to m sub L squared, h bar squared over 2I. Where, what are acceptable values for ml again?
Just plus or like 0,
Mhm.
plus or minus 1, plus or minus 2, then goes on
Yeah.
forever.
And so on. Okay. I'm not sure if I'm going to have this be a Quizlet problem or a daily problem, but you're going to have to show how you go from this to this. Okay? So you're going to have to use the Schrodinger equation, that Hamiltonian, and solve for that point. I think that's, let's see, is that what the next one is? Nope, next one's a probability question.
Ooh.
So keep that in mind. You might want to figure out how to do that.
So how to solve for E?
Yep, how to get this expression. Okay. So this is kind of cool though. This defies classical mechanics where it shows that angular momentum is quantized. That angular momentum is quantized. And this isn't true in classical mechanics. So contradicts classical mechanics. Well, not contradicts, I'm sorry. Contradicts is not wrong. Right. We should say in contrast. That's a bit different. Okay. We got about 10 minutes left, and what we're going to do now is we're going to plot some of these wave functions, and we're going to see what they look like. Okay? Are there any questions so far? No? Okay. Am I okay to move this up?
Yeah.
Okay. Let's talk about plotting psi. You're going to need a little bit more space for this. What we're going to do is we're going to make a table. We're going to have a table that keeps track of our m sub l value. We're going to have a circular representation. So where we try to draw this in 3 dimensions, it's going to be kind of tough on this 2D paper. And then we're going to have the linear representation, where we try and plot this thing. Okay, so let's start at m sub l is equal to 0. We're going to try to do the circular representation. What we're going to do is we're going to draw the center of that circle. We're going to draw the path of this circle. Crap. Not exactly how I wanted it to look. So
You're
it's
going
meant to
for
be a
like an
circle.
oval type deal?
What was that, Josh?
You're going for like an oval there, or?
No, I was going for a circle. I need to take the protractor out. I'm a winner.
It'll be like that.
All right, these are the edges of the circle.
So should we draw a circle on ours, or?
Yeah, you should draw a circle on your end.
Really?
Yeah, I already drew what you drew.
I know.
We're gonna do it. We're gonna do better on the next one.
Perfect.
That's all that matters.
Now,
Always
if
improving.
we think of our wave function is equal to EI m sub l phi square root of 1 over 2 pi, right? If ml is equal to 0, what is the value of our wave function going to be?
Bro.
So it's 0 up here, right? So it's e to the
Oh,
0.
no, I'm
1
sorry.
over 2 pi.
Right, 1 over 2 pi. What does that mean for the wave function itself? Like if we go to plot it.
The constant value.
Yep, it's going to be a constant value, and it's going to be a constant positive value, right?
Yeah.
So it's just going to be a positive value like that. The picture I draw in red is what the wave function itself looks like. Let's try to plot that out. Sorry, I got to move this over a little bit. What we're going to do is we're going to plot. We have, this is our y-axis. This is our x-axis, and we're actually traveling along that circle. So we're going to have a couple points. We're going to have pi, and we're going to go, where's our plot going to end?
2 pi.
Yeah, 2 pi. And we start at 0. What's the maximum value that we're going to have? And what's the minimum value you think we're going to have?
Pi and negative pi.
Nope, not there. What's the value of our wave function? Again?
Radical 1 over 2 pi.
Yep. We're going to go from radical 1 over 2 pi, and what do you think about our bottom?
Some negative. 1
Yeah.
over radical 2 pi.
So it's just going to be a sine curve.
In this case, looking at our plot, is it going to be a sine curve?
No.
No.
No. What am I going to draw here?
It's a straight line.
Just a straight line. Let's get a little more complicated. Let's bump it up. Let's say ML of 1. We can do plus or minus 1. They'll be the same. Actually, I want that to be centered down here a little bit more. All right, I'm going to draw a better circle now. Kind of tilt it on its side. Not a better circle. I'm always, you ever see those people who do like the speed circles or
Yeah.
whatever? Yeah.
Yeah,
Talking
they're
about
like
your chalkboard or
Yeah.
robot. Yeah, I know what you're talking about.
That's like an overly impressive skill. Like it shouldn't be that impressive, but it is.
you know how hard that is.
Yeah. Yeah, I guess that's the story of my life. Except no one thinks what I do is cool.
That's the beauty that you're having a kid. You could
Yeah.
Like, look at this.
Yeah, you know the difference.
Wow.
Okay, so when we go to plot this one, we're gonna start, this is where we're starting. We're gonna start at our maximum. It's gonna dip beneath there, pop back that way, then it's gonna go back into the circle and pop back up. If this looks terrible, it's because I drew it bad.
Looks like a duck.
A little squiggly line along here. What we're
Oh,
trying to
yeah.
do is show
What?
up
Not
those-
more chickens. Yeah.
So are you just like, so in the first, when it's 0, it's technically just traveling along the circle?
Yes.
Okay, and then in this one, it's not.
It's moving around a little bit more. It's still traveling in the path of that circle, but its values are changing. So let's go to plot this in a linear representation. 0, pi, 2 pi, and we have our max or min, and we have our max value. Okay, what's this one gonna look like?
Very odd.
Well, or let's look at where we're starting and where do we end. So this is at 0, right? What's the value of the wave function at that point?
0.
So up here, right? So this is at 0. What's its maximum value?
1/2 pi. Radical over 2 pi.
Okay, and we go all the way around the circle. Where do we end up again?
And back up there.
Yeah, so we get a point there. Halfway through the circle, where do we end up?
Negative. Radical.
What were you saying, Tara?
At 0.
Yeah, we're not at 0 at that point. 0 is where that black line is.
At negative 1 over.
Mm-hmm.
Or whatever that is.
So if we go to plot that out, that's where we look like we have a sine function. Let's go a bit further. Do one more. Plus or minus 2.
Can you go back up a little bit just to and slide the thing over?
Like this.
I got it.
Okay. Am I okay to move up?
Yeah. Thank you.
All right. Okay.
I don't know the good place to have everyone else's picture.
Yeah, I know. I keep moving it around. If I could put, I can put it on the bottom.
I don't
That's a
like
little bit
to
better.
not see everyone though.
Same here.
That's my
That would-
seeing my friends.
It makes it's tough because like when I'm teaching, I can like up on a normal classroom, I can tell when someone's confused. Here I have to like stare at everyone's individual picture to get an idea.
I'll help you out. I'm always confused. Just kidding.
I don't think so.
Just smile and wave.
Not really.
Oh, I'm letting you know we are always confused.
My old confusion's okay. It's when you're like, when you're lost at sea that it's tough.
The
Sometimes we
sea-
get out there. Bring us back.
Yeah, sometimes yeah, we'll bring it back. This one, what it's gonna look like is that, and then it zips back down over here. Goes back up. Okay. If these pictures look terrible, your book has probably a by far better representation than what we're drawing here. But I think we can still plot this last one to that earlier portion. Okay. At what points are we going to be at our maximum for our plot?
At the beginning and at the end.
Definitely at the beginning, definitely at the end, because that's right there. That's that point, right? What about here? What's this point?
Maximum.
Yep, it's maximum. What about on this plot? Where is it?
Yeah.
Right at that pi, right? Okay. What about these minimums, like this point here and this point here?
All
Where
right,
does
so like that, are those at negative 1 over radical 2 pi?
Yep, they're down here, but where are they on the x-axis?
They're pi. No, maybe.
Nope. This part's
That's at
pi. That's
Wow,
0.
okay. So then it's between, it's pi over 2.
Yep. So half of pi, and then we have another one that's right there, right? Okay. So it's good if you can look at this and get what we mean in this three-dimensional representation. Okay. Are there any questions about plotting that wave function? No. Okay. What are these points right here that are crossing an amplitude of 0? And like here and here. Actually, we'll color those in blue if I can find blue. I just have more around. No, my markers. What do we got? Oh, we got lime green. Here we go. And those are these points, right? What are those green points?
Nodes.
Yeah, they're nodes. So if you notice what's happening as we increase our ML value, we go from how many nodes in this one?
0.
To this guy?
2 to
2. What about this one?
2 to the second power.
So how many do we have in ML with plus or minus 2?
4.
4. So if you notice that every time we increase our ML value, we're increasing the number of nodes by 2. Okay. All right. So are there any questions? Oh, actually, do we need to go back to that? You okay?
I'm good.
Okay. Are there any questions you guys have?